Doctorate of Forestry.
So thank you all for being here today. I'm Matt. This is Max. We're here to talk a little bit about one of the more interesting topics we learned about this year: fiber optics. Especially, we learned about optics this year. So how lasers travel through mirrors and how mirrors affect where light travels. And one of the topics that kind of gets more specific is using fiber optic cable.
Yeah. So in the study of optics, light exists in a duality. It exists as both a wave and as a ray. And the wave is either an electric, has an electric field or a magnetic field. So then light, when hitting a surface, can either be reflected or refracted. If reflected, the angle at which the ray enters is equal to the angle at which the ray exits. So when it bounces off a mirror, it's exactly the same. And then light can travel through materials, but the light moves at a different speed in each material. The index of refraction, N, is modeled by the equation the speed of light in a vacuum over the speed of light in the material. This is used in Snell's law of refraction to find the angle at which the light ray will leave one material or enter another material. So you can see that on this graph right here. As it travels from the index of refraction 1.33, it bends outward because the index of refraction of air is smaller than the index of refraction of water. Then the critical angle is when the angle refracted is at 90 degrees and cannot escape the material, as seen in the middle graph. This allows total internal reflection to occur, which is what allows fiber optic cables to work.
Okay, so now for in terms you guys might be able to understand a little bit. An actual fiber optic cable is a cable used to transfer data between, you can go between anything really. Computers use it, it's all along the ocean floor, between different continents. It really does transfer data all over the world. Optic cables are very long, thin strands. So see in the center you have that core, that's the glass that the light actually travels through. Outside of that is the cladding. It's another translucent piece of glass that kind of keeps the light in. Outside of that, there's the buffer coating, which protects from damage and moisture. A lot of times these cables are underwater, so it does help make sure everything stays together. There's two types of that single core fiber. There's single mode and multi-mode. In layman's terms, the single mode are smaller and they can transmit data through a laser, whereas multi-mode are larger and can transmit data, light coming from an LED. Hundreds or thousands of these tiny little glass things and their cladding and their coating are all packaged together, can be put under an extra strength member, which is just another extra coating, and then all together there's the outer jacket, which kind of looks something like this. You know, you'll have something that's hard plastic that will keep it all safe and sound in there. Cables can have many more layers than just that, but that's like the basic, that's what it needs. So how does it work? You'll see the blue and the red line going through. This is a representative of the core, and it'll bounce around in there, kind of, as you'll see. When you shine a laser through the glass, you'll shine it through at this end here. It'll go through the glass and bounce around until it gets all the way to the back. The same thing happens in that fiber optic cable. It'll bounce around, the signal will go through and end up at the end. Information in a computer is at its most basic form a series of zeros and ones, which can be depicted with light as the presence of light or the absence of light. So if a computer wanted to transmit the information 110011, which is also the kill code for Max's laptop, it would flash every time there was a 1, and it would stay dark for every time there was a 0. So in the end, the computer would get that string of 1s and 0s, and would be able to interpret that. Due to the fact that the light is being shown through at the critical angle, as Max said, And the cladding, that translucent piece, helps keep the light in. The light will travel all the way through the cable at the speed of light, which is why it goes so fast. Now we have a little video. It works.
I find this a fascinating object. It's a fiber optic cable for a stereo. If I shine this laser pointer down the cable, it guides the light at the other end. These cables are used to connect our world today and are capable of transmitting information across countries and oceans. But first, let me show you how it works. I have a bucket that I've modified with a window in front. And on the other side, I put a stopper in this hole right here. I have a bottle of propylene glycol with just a little bit of creamer in it. A ring stand. And of course, a laser pointer. Now, keep your eye on this plug when I turn off the lights. That's wonderful. The light follows the liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection. As the light enters the stream, it is reflected as soon as it hits the interface between air and liquid. You can see here the first reflection, and then the second, and the third. This occurs because there's a difference between the index of refraction of the guide material, here propylene glycol, and the outside, air in this case. Recall that any time light strikes a surface, it can either be absorbed by the material, reflected from it, or pass into and through it. The latter we call refraction. It's easier to see from a top view. Reflection and refraction can happen at the same time, but if a light ray hits the surface at an angle greater than the critical angle, it will be completely reflected and not refracted. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection. To create this same effect in an optical fiber, engineers create a core of glass, usually pure silicon dioxide, and an outside layer called cladding, which they also typically make from silicon dioxide, but with bits of boron or germanium to decrease its index of refraction. A 1% difference is enough to make a fiber work. To make such a long, thin piece of glass, engineers heat a large glass preform. Its center is the pure core glass, and the outside the cladding. They then draw or pull a fiber by winding the melt onto a wheel at speeds up to 1,600 meters per second. Typically, these drawing towers are several stories tall. The height allows the fiber to cool before being wound onto a drum. One of the greatest engineering achievements was the first ocean-spanning fiber optic cable. Called TAT-8, it extended from Tuckerton, New Jersey, following the ocean floor over 3,500 miles until branching out to Whitworth, England, and Panama, France. Engineers designed the cable carefully to survive on the ocean floor. At its center lies the core. Less than 1/10 of an inch in diameter, it contains 6 optical fibers wrapped around a central steel wire. They embedded this in an elastomer to cushion the fibers, surrounded it with steel strands, and then sealed it inside a copper cylinder to protect it from water. The final cable was less than 1 inch in diameter, yet it could handle some 40,000 simultaneous phone calls. The essence of how they send information through a fiber optic cable is very simple. I could have a prearranged signal with someone at the other end. Perhaps we'll use Morse code, and I just block the laser so that the person at that end sees flashes that communicate a message. To transmit an analog signal, like voice from a phone call along the cable, engineers use pulse code modulation. We take an analog signal and cut it up into sections and then approximate the wave's loudness or amplitude as best we can. We want to make this a digital signal, which means discrete values of loudness and not just any value. For example, I'll use 4 bits, which means I have 16 possible values for the loudness. So the first 4 sections of the signal could be approximated by about 10, 12, 14, and 15. We then take each section and convert its amplitude to a series of 1s and 0s. The first bar of value 10, when encoded, becomes 1, 0, 1, 0. We can do this for each section of the curve. Now, instead of looking at the green waveform or even the blue bars, we can think of the signal as a series of 1s and 0s organized by time. And it is that sequence that we send through a fiber optic cable, a flash for a 1 and nothing for a 0. Of course, the exact method of encoding is known at the receiving end, so it is a trivial matter to decipher the message. Now, you may be wondering how a laser pulse can travel nearly 4,000 miles across the ocean. It does it without some help because the light will escape from the sides of the fibers. Look back at our propylene stream. Here's how the light attenuates as it travels. You can see here a narrow beam in the bucket that broadens a bit when it enters the stream. And then after the first bounce, the beam leaves even broader than it entered. That's because the interface with the air is uneven, and the rays that make up the beam strike at slightly different angles. When that beam makes its second reflection, those individual rays diverge even more, until by the time it reaches the third bounce, many of the rays are no longer at the critical angle and can exit from the sides of the stream. Here it happens in a few inches, but in a cable like tatting, the signal travels a stunning 50 kilometers before it needs to be amplified. Absolutely amazing. I'm Bill Hammock, the engineer guy.
So unfortunately, we weren't able to do our own demonstration of this, so we had to use the video. But that's how fiber optic cables work and how they transmit data. Any questions?
Good job.
Okay, Renata, right there.
Good.